Welcome to our tutorial on model monitoring in practice. My name is Krishnaram Kenthapadi. I'm the chief scientist at Fiddler AI, where we are building an enterprise platform for machine learning model monitoring and explainability. Together with my collaborators, Lakkaraju from Harvard, Pradeep Natarajan from Alexa AI, and Mehrnoosh Sameki from Azure AI, we are delighted to present this tutorial. You can find more information about the tutorial at the tutorial web page, which is linked here. We have included links to other tutorials as well as various resources at this website. We will also be posting the tutorial slides and video at the website as well. Let's start with understanding why we need machine learning model monitoring. Over the last several years, we have observed a variety of instances where machine learning models have not behaved as they were intended. For instance, back in around 2016, Joy Bolamwini observed that facial detection softwares, in fact, often did not detect her own face. These softwares tended to work well for light-skinned faces, but often failed for darker faces. Perhaps this motivated Joy to collaborate with Timnit Gebru on the famous gender shades work, which showed that commercially available facial analysis software had nearly zero error rates for light-skinned men, but had very high error rates for dark-skinned women. So of course, this is not limited just to, say, facial analysis. Over the last few years, we have seen a variety of instances ranging from photo tagging, web search, criminal justice, hiring, and so on, where machine learning models have exhibited biases for different subgroups. So why is this happening? We all know that there may be different types of inherent biases present in society, and often these biases could get reflected in the training data. After all, the training data is often obtained through explicit human judgments or through implicit user feedback. The machine learning models are very good at capturing patterns in the data, and in some cases, they may even amplify the biases which are already present in the data. This topic has gotten so much attention that there are even popular books written on this topic, like the ones shown here. At the same time, if you take a different dimension, which is, say, privacy, we have seen a variety of settings where privacy failures have occurred, at least over the last 2 decades, if not more. These have ranged from re-identification attacks to attacks on auditing, attacks on web search logs, attacks on Netflix challenge data sets, social networks, genomics data sets, recommender systems, so on and so forth. And fairly recently, we have seen even a paper showing that large language models tend to memorize uniquely occurring tokens in the training data. For example, tokens like phone numbers or addresses, even if they occur just once in the training data, which might be considered by the larger public as potential breach on privacy. Just like privacy, the machine learning models have also been shown to be prone to adversarial attacks. You may all have seen this famous example where if you take the photo of panda and add noise, which is imperceptible to humans, the machine learning models starts predicting a completely different class, in this case, gibbon. Perhaps this may not be as concerning, but as these models are getting used more and more in critical applications, for example, in autonomous driving settings, these become problematic. Yeah, here is an example where the ground truth is the speed limit sign shown on the left, and the model, after a small amount of noise is added to the input, predicts that it's a stop sign. These are not just limited to digital photos or digital videos. It has also been shown that such attacks are applicable even on physical world stop signs or physical world objects. In this example, the one shown on the top is a stop sign with very slight changes, and it was predicted to be a different class. And similarly, the one at the bottom was predicted to be a stop sign with very small changes. So more broadly, if you take a step back, the machine learning and AI teams today face a variety of challenges with their models. These range from lack of model transparency to model decay, model bias, challenges with meeting compliance, and so forth. For instance, so we have seen challenges such as the ones faced by Facebook in the context of how Facebook's models work and the lack of enough transparency on those. Or we have seen challenges with the models degrading over time, whether it's due to the pandemic or other real world condition changes. So of course, we just discussed challenges with bias in the models. Likewise, often compliance is also a key challenge when it comes to highly regulated domains. The underlying reason for many of these aspects is that the machine learning models often are highly opaque. There may not be explanations of how the model is behaving. Often, even the model developers themselves do not have a good understanding of how the model is behaving, which features are important, whether there are biases in the prediction or the performance of the model. And more importantly, in the context of this tutorial, often there are not enough tools to monitor the models once they are deployed. As a result, the practitioners often don't have visibility into how the models are behaving once they are deployed in production. This affects a variety of stakeholders, ranging from, say, business users who wonder whether they can trust the machine learning or AI models, to data scientists who are perplexed as to how the model is working in practice, or auditors, regulators, and other interested entities who wonder whether the decisions made by the model are fair or not. So here are some quotes we have seen from different personas who are involved with operationalizing machine learning models. For example, a quote from a chief scientist discusses how model drift or changes in the real world conditions and the lack of timely detection of such changes cost over $500,000. Often the machine learning practitioners encounter a lot of time before they're able to detect and thereby troubleshoot the problem. Sometimes they're worried whether they will have to go and testify in front of legislators, because even they themselves may not have a good understanding of how the models are behaving, and so on and so forth. So with given these concerns, so the area of what's often called as model performance management has become more and more accepted amongst the machine learning practitioner community. By model performance management, or broadly model governance, what we are referring to is how to understand the behavior of the model, both offline before the model is deployed and online once the model is deployed. During the offline stage, we may want to understand whether there are any gaps in the training data used to train the model, whether there are biases in the training data, whether there may be feature quality issues. Can we understand the behavior of the model as a whole? Can we construct model cards or data sheets associated with training data? Can we discover failure modes of the model, the segments where the model cannot be relied upon, so that we can then fall back on human experts for those regions? Can we discover slices where the model may be poorly performing so that we can perform root cause analysis and perhaps include more appropriate training data, or retrain the model, or even develop a separate model, and so on. During the online stages, we may want to compare how a new model behaves as compared to the existing model during A/B testing. In addition to understanding whether the new model provides improvements overall, we may also want to understand whether the new model improves for all interested groups of people, not just overall. And finally, we may want to monitor the model over time to detect whether the model is degrading in performance, degrading with respect to other dimensions like bias, explainability, adversarial robustness, and so forth. And together with all of this, once detected, we then want to understand what may be causing these issues and be able to come up with a way to fix those issues. So if there is one takeaway from this tutorial, it's that we have to consider the online aspects as much as the offline aspects. Monitoring deployed models is at least as important as validating and vetting the models before deployment. Just like we encounter issues during model validation, we may also encounter similar issues once the model is deployed. We have to think about not only accuracy of the model, but also dimensions like bias or adversarial robustness, or perhaps any potential privacy breaches, so on and so forth, once the model is deployed. With this introduction, in the rest of the tutorial, we will be briefly covering 3 dimensions. First, we will describe what are the nuances or an overview of monitoring deployed machine learning models. We will categorize that into 2 parts. The first part will focus on model performance degradation and the common issues underlying such degradation. The second part would focus on what are the things to worry about beyond just model performance itself. These can include bias, feature attribution changes, adversarial robustness, privacy violations, and so on. Then in the second part, we will present a few case studies to illustrate how this is done in practice. And finally, we will conclude with a few key takeaways from this tutorial. For deeper discussion of some of these topics, please refer previous tutorials. For instance, a tutorial on responsible AI, which we presented at FACT and other conferences last year, and many other similar tutorials on these topics. Thank you. In this part of the tutorial, we will first give an overview of the issues observed during monitoring deployed machine learning models, starting with some of the model performance degradation related issues. One of the common types of issues that is observed is drift of different types. So by drift, we mean changes in certain distributions. For the purpose of this section, let's assume that the model under consideration is a binary classification model. So for example, here is a model which is represented in a 2-dimensional space with perhaps say 2 features. The blue and yellow correspond to the labels of the model, correspond to 2 different classes. And here is the decision boundary and the training data that is used to train the model. Let's consider the probability of the target variable, in this case, the color of the circle denoted here, given the input X, which is represented as the feature vector here. First type of drift is what's often called a concept drift, or sometimes called real concept drift. Here, the relationship between the target variable and the input features changes. So in other words, the probability of y given x changes. This can occur due to changes in perhaps real world conditions, even if the input does not necessarily change. Like, for example, in this illustration, we can see that the distribution of inputs has remained the same. The points are where they were, and even the most of the class labels are as before, but the relationship has changed. So another type of drift is called a data drift. So here the data distribution, the input data distribution, or the features themselves change, even if the relationships between the target variable and the input features may not have changed. So often this may not be as much of a concern. Like, what we really care about is being able to identify concept drift as opposed to just data drift. There are also other terminologies used in this community. So one is label drift, wherein the probability of the label distribution changes. The other is feature drift, wherein the probability of the input data, or P of X, changes. Either of these doesn't necessarily mean that concept drift occurs. It is possible for just the label distribution to change or the feature distribution to change while the relationship remaining intact. Let's consider a setting where the label drift happens. This, as I just mentioned, this doesn't necessarily mean that the concept drift has occurred, and as a result, this does not necessarily affect the model's accuracy, but it can still affect the underlying business. For example, if the ratio of people eligible for loans suddenly increases or decreases, that may lead to a loss of opportunity or decline for business in the case of a lending company. So likewise, the feature drift may not necessarily correspond to degradation in the model quality, and often some level of drift in the data distribution is expected over time. Just like label drift, this can also still lead to certain types of issues. For example, if the model starts seeing data it has not seen during training time, it may not necessarily behave as expected, even if the underlying relationships have not changed. Finally, the terminology virtual drift refers to the setting where the different types of drifts may have happened. For example, the relationship may have changed, but the decision boundary used by the model may still work as before. So as a result, that may not have as much of an impact as far as the model itself is concerned. Let's make this concrete using a loan application model. Here, let's look at when concept drift can occur. Consider a setting where the income level that was considered creditworthy earlier may be now considered riskier. So this can happen in the case of macroeconomic factors, which may cause lending to be riskier than before. And as a result, there may be a higher standard for deciding whose loan application should be approved and whose should be rejected. Another setting is label drift. An example of this might be a larger proportion of creditworthy applications may start showing up. This may simply be because the model may have been trained on the overall population, but may have been deployed perhaps in a more affluent area. As a result, the model starts seeing applicants who are more affluent and consequently maybe more credit worthy than the general population. The third example is feature drift. This is a setting where the incomes of many applicants may increase or decrease, or we may get more applicants from one particular geographic region or one particular demographic. Again, this might also have a tangible impact on the underlying business metrics. Next, let's look at what are the factors that may lead to such types of drift. Broadly, we can categorize this into two types. The first one is what I have denoted here as real change. So this corresponds to a setting where the label distribution or the feature distribution can change. For example, there may be a product launch in a new market, and as a result, the input distribution as well as the output distribution may be different. Or in the case of, let's say, a pandemic or a competitor launching a new service, the relationship between the target variable and the input features can change, or the concept drift can occur. In these cases, often we may have to retrain a model, or perhaps come up with maybe newer features, different set of features, or collect different types of training data and train a different model possibly. The other type of trigger is the broad class of issues which are called data integrity issues. This is a setting where the underlying foundations have not changed, but the data that is fed into the machine learning model may be corrupted. One setting where this can happen is the correct data is obtained at the source, but due to some bugs in the data engineering pipeline, things might get misrepresented. For instance, somewhere in the pipeline, values for age and debt to income may have been swapped, and that might cause an issue. Or it's possible that somebody might have made a change from, say, inches to centimeters for some measurement, but that may not have been reflected downstream. And as a result, the machine learning model might expect the value to be in inches, but instead is receiving the value in centimeters instead. The second type is incorrect data. It may be entering at the source itself. This could be due to, let's say, a bug in the front end. Let's say a website form accepts even if a field is left blank. As a result, that entry may become missing or may get corrupted. So next, let's discuss how we can detect these issues. Again, like we want to broadly group this into two buckets. The first bucket corresponds to the setting where we may have access to labels, and the second bucket corresponds to the setting where we may not have access to labels, or we may have to make decisions solely based on data distributions and the changes in these data distributions. Under the first category, we tend to apply this kind of techniques when we have access to ground truth or labels. If there is a mechanism to obtain ground truth labels almost in real time, we can keep track of different quality measures of the model almost on a real-time basis, and see whether some of these quality metrics may be dropping over time. There are a variety of, again, different types of techniques to achieve this. I would encourage you to take a look at this excellent survey on concept drift adaptation. But let me emphasize that in many real-world conditions, we may not get ground truth labels immediately, or even if we get ground truth labels, it may be after a subsequent period of time. For example, if you consider lending settings, we may not know the ground truth until after the borrower has repaid the loan or defaulted on the loan. And this holds true for many other real-world settings as well. In those settings, we may still want proxies to gauge whether the model may have degraded in performance. There are different types of such proxies. One proxy which is kind of intriguing is one where we look at the features that are important for the model and see whether the set of important features is changing over time. If the set of important features is changing, or the relative importance between these features for the model prediction is changing over time, it could be an indication that concept drift may be occurring, even though we may not have access to ground truth labels, and even though we may not be able to measure the model accuracy directly. Next, let's look at the second category. First, let's consider the setting where it might still be a supervised learning setting, like say binary classification, but we do not have access to ground truth labels. So in this case, we may want to measure changes in the distribution of underlying variables. For instance, the distribution of features or the distribution of the prediction probability itself. There are several different statistical measures commonly used to compute these differences, such as Jensen-Shannon divergence or KL divergence, population stability index, and so forth. These can be applied either on the prediction probability distribution or on the feature distribution themselves. While these are parameterized in some sense, one could apply non-parametric tests, such as the Kolmogorov-Smirnov test, to determine if there may be a drift in the data. Next, let's consider the setting where we may have unsupervised learning settings. Once again, I would not be going into the details, but I refer you to this article which provides an overview of unsupervised drift detection methods. There are different types of trade-offs of this class of methods. They can often be more accurate, but they tend to provide an overview of the global picture, and as a result, they may miss gradual drift or sensitivity issues associated with the model. In addition, often this class of methods may not be easy to explain to a non-technical user, such as a business decision maker. Next, let's discuss what do we do once we identify different types of drift issues. Again, like here we are divided into two buckets. The first is figuring out whether data integrity issues may be causing the problem. The second is, if not, to identify what may be the underlying root cause for the changes. In terms of data integrity, again, like there are either data integrity, or you could also think of them as monitoring for outliers. Unlike in non-machine learning applications, the machine learning applications tend to be very forgiving. And even if incorrect data or missing data is fed to the machine learning model, the model may still produce an output, just that it may not be as reliable as before. So there are different types of data errors. These can range from missing values, or say range or type mismatch, or even schema mismatch, changes in the unit of measurement, swapping of maybe two features, and so forth. Again, this can be due to data pipeline bugs, or possibly changes in some parts of the system which may not be reflected in other parts of the system, or even possibly changes in the business itself. The second category here is what we call drift analytics. So this is one where we want to understand the root cause of the drift by performing attribution to different possible causes. For example, here we are seeing a screenshot from the root cause analysis of drift using Fiddler's model monitoring platform. So here in the topmost chart, we see the drift in the prediction probability. And once we have identified such a drift, we then want to attribute that drift to different features, in taking into account the importance of the features themselves. And then we may want to go deeper and look at the changes in the features themselves in terms of the changes in the feature distribution between two different points of time, and try to find out whether there may be outliers or other issues that may be causing this. And then once we identify such changes in the feature distribution, we may want to then slice and dice the data by trying to determine whether the change is predominantly coming from, let's say, one geographic region or one subgroup of the data, as opposed to changes occurring across the entire spectrum. Having identified the root causes, let's look at what may be different types of ways to fix the issues. So one type of fix is to update the pipeline. This works in the case of data integrity issues, wherein we can make sure that the schema changes are correctly reflected or the violations are fixed and so forth. The second type of fix might be one where we may decide to retrain the model, or perhaps adapt the model to a subclass or a different setting. This may involve perhaps reweighing the data points or applying appropriate business logic and so forth. The third category is one where we may want to think of this as managing the model as a whole. This might involve perhaps archiving models on a regular basis, or retraining on a regular basis, and comparing one model versus other models which may be related, and so on. So with this context, let's now look at model issues for deployed models beyond model performance. So what do we mean by beyond model performance? This can range from, say, notions like bias and fairness, or transparency, explainability, privacy, or robustness, and so forth. And the reason to consider these different dimensions is that even if the model continues to maintain accuracy, it's still possible that the model may start exhibiting differential performance for different groups over time. And as a result, certain subgroups of the population may not be experiencing the same level of quality as during the model training or model validation time. So specifically, let's start by focusing on fairness and bias. First of all, how do we go about approaching fairness or bias in a practical setting? So here there are two broad notions. One is from the perspective of the policy aspects, and the second is from the perspective of technology aspects. When we say policy or process aspects, so it starts with identifying what are the goals for this product, what are the acceptable trade-offs between, say, accuracy and any potential bias present in the model. We may want to get all the relevant stakeholders as part of this decision-making process. And this should include those who may also be impacted by the model. It's important to make sure that when we collect the set of stakeholders, there is representation from people with different demographic backgrounds, different lived experiences, different disciplines, and so forth, so that we do not have any blind spots when deciding what are the right choices for the model to start with. So of course, this involves identifying the relevant stakeholders. So once we have addressed these issues, then from a technology angle, we may want to decide what may be the most appropriate fairness notions and corresponding metrics for the specific machine learning model setting. So once again, the fairness notion has to be decided by taking inputs from all relevant stakeholders and the application context in mind. Next, we may want to analyze and evaluate the system, both the machine learning model and any associated business logic surrounding the model. Then if we observe any issues, we may then want to figure out how to mitigate the issues. And the key aspect I want to emphasize here is that we not only need to do this during model validation time, but also need to monitor this continuously and have plans for escalation if certain types of biases are observed once the model is in production. What should the remediation be? And it's good to think through these escalation plans beforehand. And notions like auditing and transparency also go hand in hand with all of these issues. So more broadly, we can think of fairness being incorporated into all aspects of the machine learning lifecycle. This starts with the problem formation, asking ourselves whether using a machine learning approach is even desirable and ethical for the specific problem setting. Next, when it comes to data set construction, we may want to ensure that we have data representative of different groups, and if there are any biases in either labels or features, we may want to figure out how to mitigate those biases. Then during model training, we may want to incorporate fairness constraints. And similarly, during testing, we may want to test the model for performance for different groups. During the time of deployment, starting with A/B testing, it's often desirable to understand whether the model has unequal effects across different users. Even if during A/B testing, we notice that the new model performs better than the old model overall, we still want to understand whether the model has improved performance across all subgroups. Also, we want to know whether the model is deployed on a population for which it was never intended. The model may have been trained and evaluated on an altogether different population or different purpose, and we may be deploying in a completely different setting. While in certain cases it may be fine to do this, it's important to be cognizant of that change and ensure that the model still works well for this new population. Finally, we may want to understand whether the model has any feedback effects which can result in increasingly unfair outcomes. A classic example of this is the Tay chatbot that Microsoft launched around 2014-2015 timeframe. And because of feedback effects, this chatbot started exhibiting biases very quickly. And more broadly, we want to keep monitoring the deployed model for different types of bias metrics. So let's look at how this can be operationalized from an engineering angle. So here we are again showing the same kind of machine learning lifecycle, but in a linear form here. All the boxes in yellow correspond to the steps where we may want to incorporate fairness interventions. First, at the time of preparing training data, we want to measure any bias in the training data and decide whether we want to mitigate bias by applying different pre-processing techniques. Similarly, during the time of model training as well as model tuning or hyperparameter optimization, then when we decide to A/B test or deploy the model, again, we may want to check whether we want to apply post-processing bias mitigation techniques. And most importantly, once the model is deployed, we still want to measure and monitor the bias metrics over time. So all these steps are perhaps important, and often there tends to be a lot of emphasis on everything to the left of this dashed line, which corresponds to the offline aspects and not as much on the online aspect. Let's look at how this is operationalized from a machine learning deployment setting. So for this, here is a screenshot from Amazon SageMaker. Specifically, this is a screenshot which shows how one can monitor bias for a deployed model over time. Here, the model developer or the stakeholder has chosen two different bias metrics, difference in conditional outcomes and conditional demographic disparity in labels. And they have also set a threshold shown by the orange line here. And whenever the observed bias measure exceeds the threshold in a statistically significant manner, the model developer can choose to get alerted so that they can then decide whether any intervention is needed and any corrective action needs to be applied. So this is done as part of Amazon SageMaker Clarify and SageMaker Model Monitor. If you're interested in details, please refer our papers which appeared in KDD 2021 and 2022 for details. Next, I also want to show how we can similarly monitor drift in the behavior of the model itself over time. So here again, in the screenshot here, we are showing how one can keep track of the importance of different features over time. Specifically, here we are looking at importance of one of the features called A14, associated with a model trained on the German credit data set. And we are looking at how the importance of that feature changes over time across different predictions performed by the model. So here the importance score is obtained using a variant of the Shapley values, or using a variant of the SHAP technique. At the bottom, we see the chart of the different features ordered by importance, and it may not be visible here. We also show whether certain features have gone up in ranking or gone down in ranking. That can also be an indication whether certain features may be becoming less important or more important over time. And depending on the application context, one could again take certain corrective actions. So once again, for details, please refer our paper. So this concludes the discussion about bias and fairness in deployed machine learning models. Next, we will discuss some of the challenges with keeping track of explainability over time for deployed models, and also how to ensure that the deployed models are not prone to adversarial attacks.
Now let's talk about how to monitor the behavior of deployed models via their interpretations and explanations. Before we get into the details of how and why we need to do this, let's first try to understand the utility of model interpretations and explanations. Several of the prior works have argued that model understanding can be very critical in various real-world applications, particularly those involving high-stakes decisions, whether it is healthcare or lending, and many more such high-stakes applications, right? To understand how model interpretations and model explanations can be beneficial in these settings and more, let's take some use cases or examples to illustrate their utility. Okay. Now, for example, let's say that we are looking at a predictive model, which is potentially buggy, but this model basically takes as input images of animals and then produces predictions about what animal is in the picture. In this case, if we provide the input image of a Siberian husky, you see that the prediction that's coming out of this model is Siberian husky, right? So far, everything looks good. Okay. But upon careful examination of how this model is generating this prediction, for example, seeing what are the pieces of the image that the model is focusing on, we might observe a lot more about what the model is doing, or infer a lot more about what the model is doing. For example, in this case, we observe that the model is actually focusing on the snow pieces within the image, indicating that, it is using snow to determine if the animal in the picture is Siberian husky or not, right? So this model is indeed a snow detector, but it's not looking really at the features of the animal when making a prediction about which animal it is, right? So since this model is relying on spurious features to make this prediction, it is a clear indication to the developers, engineers, and scientists building this model that they may need to fix the model further so that it is not relying on spurious features and they're not building snow detectors. Okay. In this case, model understanding has facilitated debugging, or it has helped facilitate debugging of the model. Now let's think about another scenario where there is a loan applicant and there's a predictive model which takes all the details of the loan applicants and determines if the applicant should get a loan or not. Okay. Loan officer is the decision maker who is at the receiving end of these predictions. Now, if this is the setting that we are looking at, so far everything looks reasonable, but if we get more understanding about what are the key features that this model is focusing on, then we can say more about the model, right? So in this case, what we observe is that the model might be focusing more on race and gender when making this decision of denying loan to this applicant. So this prediction is biased since it is relying on features such as race and gender. And a loan officer who is able to see this can actually decide not to give any kind of weightage to this prediction and rather make his or her own decision about this particular applicant, right? In this case, model understanding is helping us facilitate bias detection. Okay, so if the model is relying on features such as race or gender. Now let's consider another scenario where, again, there is a predictive model which takes as input details of loan applicants and then predicts if the applicant should get a loan or not, right? In this case, the end user is the loan applicant himself. So the model is telling this person whether he or she will get a loan or not. In this case, the loan has been denied, right? So just providing that input of your loan has been denied is not very useful to the applicant, but instead, if we provide more understanding as to what the applicant can do, for example, increase your salary by some amount and then pay your credit card bills on time for next 3 months to get a loan, if we say that to the applicant, then they do have a means for recourse, right? So that is actually quite helpful to the applicant, and then the applicant has something to work towards or work with in order to go back, fix the sort of the weaknesses in his profile, and then come back and apply for a loan. So in this case, model understanding is helping us provide recourse to individuals who are adversely affected by model predictions. Okay. Now, let's take another scenario where there's a predictive model which takes as input a bunch of patient data about patient demographics, about symptoms that patients are facing, prior health conditions, and so on, and outputs predictions in the form of if a given patient is healthy or sick, right? Now, if we generate a bunch of such predictions and show them to a doctor, the doctor really has no way of knowing how much to rely on each of these predictions or how much not to rely on them. So in this case, if we provide a big picture view of like the patterns that the model is using when making predictions, for example, as you can see on the screen currently, the model is basically using reasonable features such as symptoms such as cold and cough to see if a male patient is sick. But in the case of female patients, the model is relying on ID numbers to determine if a patient is sick or not, right? So in this case, this understanding that the model is using irrelevant or spurious features on female subpopulation, while it is using relevant features on male population, that understanding will help the doctor determine that this model's predictions should not be trusted on the the female population. Yeah. And in this case, model understanding has helped the doctor assess if and when to trust model predictions when making decisions. And such an understanding can also be used by authorities, whether it be FDA or any other agencies, to sort of determine if a model is ready to be approved in order to sort of cater to a broader population. So, in this case, if the authority sees that the model is basically using spurious features such as ID numbers on female subpopulation, then they may deem that this model is not ready to be deployed at a broad scale because it is relying on spurious features for like half the population, basically, right? So in this case, model understanding can help us vet models to determine if they're suitable for deployment in the real world. Okay. All right. So clearly, model understanding has a lot of utility in terms of enabling debugging, bias detection, pre-course determining if and when to trust model predictions, and also vet models to assess suitability for deployment. In enabling a lot of such use cases, model understanding is serving several stakeholders who could be end users like loan applicants, or decision makers like doctors and loan officers, or regulatory agencies such as FDA, European Commission, and of course, researchers, scientists, and engineers in order to debug these kinds of models, right? Given that there is so much potential in terms of the use cases that model understanding enables, let's talk a little bit about what are the popular approaches to actually achieve model understanding. So, one of the commonly employed strategies is to build models that are inherently predictive. For example, a lot of the model classes, such as whether it be, models that are linear models, whether it is logistic regression or linear regression, whether it is shallow decision trees, or whether it is rules with, fewer predicates and conditions. So these are all models that people can look at and understand the rationale or the logic of the model, and are often referred to as inherently interpretable models, right? So such models can not only make predictions, but they're also easy to understand for the different kinds of stakeholders and end users, right? So if we think about such models, now if we try and connect it back to the monitoring angle and say, okay, so we have built such a model, so now the model is running on sort of like streaming data, and there may be a risk that the data has shifted, right? So what do we do? How do we monitor such kind of a model? In order to monitor inherently interpretable models, here are some considerations. Okay, so first of all, these models are transparent and interpretable, and these models are sort of not changing with the data, unless of course we retrain them, right? So there is new data coming in, and these models are very easy to understand and transparent, and what you see is what you get, right? So nothing new is, or out of the box, is going to happen in the case of these models. For example, if there is a decision tree, the decision tree will invoke the same set of rules in order to make predictions on any given data point, right? So we have clear understanding of what the model will do, irrespective of what the data is. And that's what we are trying to say here. And this basically implies that even if the underlying data changes, the model behavior would remain the same, right? Because we see the model in its entirety, okay? There are no more surprises. So given that, we, at least from the sort of model behavior via our understanding of the model's perspective, we don't need to do a lot in terms of model monitoring with models that are inherently interpretable, right? Now, another approach that has commonly been employed in the past, half a decade or so, in terms of model understanding, is applicable to more complex models, whether it is very complex deep neural nets, or whether it is black box models that we don't even have access to. In such cases, the way we can understand the model would be to basically explain pre-built models in a post hoc fashion. That is, we may have either a black box model that we have no access to, or we may have an extremely complex deep neural network. So such kinds of models, we can pass them through an explainer algorithm, which explains these models in a post hoc manner, which means it basically generates explanations of these models using simpler models that people can interpret. For example, again, linear models, or shallow decision trees, or like a smaller subset of rules and so on. So we are just breaking down a complex model into simpler models that are easy to interpret in this kind of an approach, right? So before trying to get to the notion or the point of how can we then use these kinds of post hoc explanations to monitor model behavior, let's first try and understand what are some high level categorizations in terms of post hoc explanations, right? So these explanations at a very high level can be divided into local explanations and global explanations. Local explanations are geared towards explaining individual predictions of models. So you explain a single prediction at each time. That's what a local prediction does. And in doing so, they help us unearth biases in the local neighborhood of a given instance. And they help us vet if individual predictions are being made for the right reasons or are relying on relevant features and not spurious or irrelevant ones, right? Global explanations, on the other hand, aim to explain the big picture view or the complete behavior of a given model. And in doing so, they actually shed light on these big picture biases which affect larger subgroups in the data, not just individual points in the data. And in doing all of this, they can help us vet if the model at a high level is suitable for deployment, right? So those are two high level categories. So we'll get into the details of some algorithms which are popularly used to generate local explanations as well as global explanations now. Okay. One of the most commonly used and one of the simpler algorithms to sort of generate local explanations is LINE, which stands for Local Interpretable Model Agnostic Explanations, right? The thing that LINE does is actually this, is essentially this, right? So let's say our goal is to basically explain the prediction of this point here, which is denoted by a red plus mark, okay? What we do in this algorithm is we first sample points around this point, okay? So we essentially perturb that point slightly and then generate a bunch of samples around that point whose model prediction we would like to explain, okay? Then what we do is we use the model that we want to explain to predict the labels for each of these sampled points that we have generated around X, okay, or Xi, right? So which basically means we also get the labels for each of these points, which class they belong to according to the labels assigned by the underlying model. Now, then what we do is some points within these sampled points are closer to Xi and some are farther away from Xi. So we then weigh these samples according to the distance to Xi, and points that are closer to Xi get higher weightage and points that are farther away get lower weightage, okay? Then essentially after doing this, what we do is we learn a simple linear model on these weighted samples. For example, a weighted linear regression or a weighted logistic regression, we fit such a model on these weighted samples, and the resulting model is basically a local explanation of the underlying complex model, right? So that is as simple as it gets. So just to summarize, what we do is if we were to explain the prediction of this point Xi, you take the point, you perturb it a little bit and generate a bunch of points in the neighborhood of this Xi point. And then we label each of these points using the predictions given by the underlying model. And then we fit a weighted linear model on these points and the model predictions. And that linear model essentially serves as a local explanation of the underlying complex model, right? So we are essentially doing a local function approximation here. Now, another popular method, which also outputs feature importances, but uses more game theoretic style approaches is called SHAP. But essentially, even with SHAP, we get as output feature importances that are local. So again, we get a local explanation from SHAP as well of the underlying complex model. Okay. Uh, some of the other approaches that are commonly used to actually generate these kinds of local explanations, which are feature importances, are gradient based methods. The idea here is to essentially compute the gradient of the function that we are trying to explain with respect to individual input points, that is each of the features of the individual input points, right? So for example, if we want to understand which features or which parts of this image are influencing the prediction strongly, then what we can do is we can compute the gradient of the underlying complex function that we want to explain with respect to each of the input pixels of this image, right? Of course, just computing this vanilla gradient can result in some challenges. For example, the resulting gradients are sometimes noisy and unstable, which means even if we make a small change to the image, the gradients that you compute might vary drastically. So in order to address some of these instability problems, newer approaches such as smooth grad have been proposed, where the idea is to smooth the gradient by averaging the gradient across a small neighborhood of points, right? So you can take a point and then perturb the point slightly, generate a few perturbations around the point. Now compute the gradient of the function with respect to each of these points, and then compute the average gradient, and that will basically serve as an explanation, and it addresses the problems of noisiness and unstable or instability of vanilla gradients, right? So these are another set of approaches to compute local explanations, and all of these that we discuss, whether it's LIME or SHAP or gradient based methods, they all output a vector of feature importances that people can use to sort of understand what features the model is relying on locally. Okay. Now, given that these are different kinds of post hoc explanations and local post hoc explanations, how can we monitor models using these kinds of explanations, right? So first of all, hopefully the kind of depth of information that these explanations can give us about model behavior convinces all of us in realizing that it is important to continuously monitor local explanations output by the aforementioned feature attribution based methods to see if the model uses spurious features to make predictions on any newly encountered data, right? So typically the way people use a lot of these explanation methods is they can help us understand what features is the model relying on. While the model might be relying on appropriate or relevant features for points in the data that it already had seen, that may not always be true for newly encountered data, right? So for the prior data that the model has looked at, has been trained, it might be using relevant features, but then when there is a shift that occurs in the data or new kinds of data points that come in, then the model may start looking at irrelevant or spurious features when making predictions about them. So that's exactly what we need to monitor for using local explanations, right? So this is precisely where the role that local post hoc explanations can play in terms of monitoring models. So basically, whenever a new point is encountered once the model is deployed, generate local post hoc explanations for the new point as well, and then just check what features is the model relying on for all these newly encountered points, and if those are relevant features or if those are spurious features, right? That monitoring needs to be done. Okay. Now, the other category of explanations that are also quite popular are global explanations. And I'm going to discuss just like an example of one way of generating global explanations. By the way, there are also other ways of generating local explanations that we did not entirely get into the details of, but the goal here is to just give an example of how can we think about model monitoring using these explanations. So we are just taking some examples of certain explanations. Okay. Similarly, in case of global explanations, we'll try and see how such explanations are generated using model distillation. Okay, so let's say here we have a black box model. Okay, so which we may not have access to, and we have a bunch of data which will be provided or which can be provided as input to this model, and then the model in turn can generate labels for each of these data points. So we have some input data, we have a black box model that is queryable, and it will produce predictions of any of the data points that we throw at the model, right? We can actually use this information and pass it through an explanation algorithm, which in turn tries to approximate the behavior of the black box model using a more simpler interpretable model, which is optimized to mimic the model predictions on the data we provided as input, right? So essentially, we'll be able to, or rather the idea behind model distillation is that we take the input instances, we take the model predictions and fit a simpler model, which basically mimics the model predictions on those data points that we provided as input, right? So for example, prior work has used decision tree or rule-based models as these interpretable models. So you take the input data, you take the model predictions from the black box model, and you essentially fit a decision tree which mimics the predictions of this model, right? So that is what is referred to as model distillation. Now, given that that's how we generate global post hoc explanations, how can we think about model monitoring via these kinds of explanations? So model distillation approach specifically to generate global explanations often generates explanations that are data dependent, right? So as we just talked about in the previous slide, the fitted interpretable model like the decision tree essentially is being fit on the input data points and the corresponding model predictions, right? So if the data itself changes, then you would see that this interpretable model that you're fitting as a global post hoc explanation will also change, right? So which means the learned tree or the learned interpretable approximation will change if the underlying data shifts, okay? Now, it is important to continuously generate these global explanations at various time points and monitor them to see how the model is behaving on the data continuously, right? So when the model is built, obviously we'll use the data that the model was built using, and then the corresponding model predictions, and then we'll fit a decision tree to approximate the behavior of the underlying model and see some high-level patterns about it, right? Now, once more data comes in, we again need to fit this decision tree so that we see now the predictions that are being made by the model on this new kind of data, and to make sure that the model is still using relevant features and not spurious ones even on this newly encountered data. Okay. Now let's talk about monitoring adversarial robustness of machine learning models. While machine learning models these days are often quite accurate, the predictions resulting from these models are also known to be brittle. Okay? To illustrate, let us consider this classic example where there is the image of this piglet, which the model is classifying rightly with very high accuracy as pig, right? Now, if we add some imperceptible noise to this image and generate a new image, which to a human eye looks exactly the same as the original image, you see that the model's prediction has drastically changed, and now the label being given to this point is of airliner class with a very high confidence, right? So this has been a popular phenomena that has been observed in several works. That is, if you add a small amount of noise that is almost imperceptible to the human naked eye, the resulting images often get tagged or labeled as a different class with high confidence, right? So this demonstrates that these predictions are actually very, very brittle. So now how do we think about this in the context of model monitoring, and how do we actually measure the brittleness of the models is something that we'll talk about now. Okay? In order to measure the brittleness of the models, what we can do is compute the expected worst case loss for the model. Okay, so how do we compute that? What do I mean by that? The expression that you see here is basically computing the perturbation delta of a given point x for which the loss of the model turns out to be the worst, okay, with respect to that point x. So now if we can compute this with respect to all the points in the data distribution and then take the expected worst case loss. So this is the worst case loss for one point x. If we basically compute this for all the points in the data distribution and then take the expected worst case loss across the data distribution, then that provides us with a measure of the brittleness of the model, right? So in some sense, higher the loss, more brittle the model is, and therefore less adversarially robust the model is. Okay. So the thing that we want to compute here to measure the brittleness or the adversarial robustness of the model is the expected worst case loss of the model. Okay. Now, it is also important to continuously monitor this adversarial robustness of models on any newly encountered data. Why is this important? This is important because while the model might be adversarially robust in those parts of the feature space which are already encountered during the training process, this may not be true for other parts of the feature space which may be encountered only at test time when there is a shift in the data, right? So that's why it's important to compute this expected worst case loss of the model continuously so that we can ensure that no matter what data is coming in, the model still remains adversarially robust.
Hi, everyone. I'm Pradeep Natarajan, Senior Principal Scientist at Amazon Alexa AI. Today, I'm going to talk about error detection in large-scale conversational assistants through offline models. To quickly introduce Alexa to you folks and the systems underlying it, there are 5 key components to Alexa: the wake word detection, the automatic speech recognition, the natural language understanding module, the text-to-speech, which outputs the response, and then the Alexa voice service that allows developers to build skills and experiences that leverage all of these other technologies. So if you look at the sequence of modules that are invoked when you go and talk to your Alexa device, say you say something like, Alexa, play Bad by Michael Jackson. What happens is there is a wake word model running on device that's listening for the word Alexa. And as soon as that model triggers, it captures the audio and invokes the conversational assistant. The conversational assistant then calls the automatic speech recognition system that converts the audio stream to text. And then it calls the natural language understanding system that does 2 things. First, it understands the domain and intent of the utterance. For example, that this is a music domain utterance and the intent is play music intent. And then it also recognizes the entities that are named and resolves it to the right entity in our database. For example, the artist name is Michael Jackson and the album name is Bad. And then potentially retrieves the entity from your Spotify playlist or something like that. Once these are done, the next step is to generate the result and then render the result through the text-to-speech module. And that produces the response, playing Bad by Michael Jackson, and then the song gets played. So if you look at the wake word detection model, we have a multi-stage convolutional neural network-based model running on device. For those of you who are from a computer vision background, This architecture looks quite familiar. And then for the automatic speech recognition system, we have models that are essentially outputting multiple different outputs. For example, the language identification, the transcription network that produces the text from the audio stream, and so on and so forth. The natural language understanding model, as we just now discussed, applies a series of models for classifying the question, for generating the answer candidates, ranking the answer candidates, and then passes off the ranked answer to the downstream text-to-speech system. And in terms of generating the answer, we search through multiple databases we have, for example, a knowledge graph, Wikipedia, web documents, so on and so forth. In terms of the text-to-speech, we again have a neural net-based model that takes the output that is generated by our model and then converts it to a audio response that you hear. So if you look at this multi-stage pipeline, what are the possible sources of error? Failures can occur in each stage of the pipeline. Error patterns are often related to specific design and modeling choices we make for these modules. And these errors are also relatively rare and quite difficult to identify in an industry-strength conversational assistant. So I'm going to present two use cases in this talk for monitoring and detecting errors in our online system through offline models. The first use case focuses on detecting errors in the domain decoupled NLU model that I'm going to describe next. And the second use case focuses on isolating sources of error, like whether it's the wake word or the ASR or NLU or TTS that resulted in an error in the multi-stage processing pipeline. In both of these cases, we are going to leverage offline transformer-based models to detect errors in the online system. For those of you not from an NLU background, transformers are among the most performant models that has been used in the community in recent years. They have extremely high accuracy, but they are also typically have large parameter counts that makes them somewhat slow for many online applications. So in terms of detecting and correcting errors in the NLU system, first I want to give you some introduction on how an NLU system is designed and why we make those design choices. So with a large-scale conversational assistant, name it, whether it is Alexa or Siri or Cortana, they all process billions of utterances every week. These utterances are typically partitioned into domains such as music, movies, weather, wiki, etc. And the customer experience and model artifacts for each of these domains are managed by independent teams. So to illustrate, this is how the modularized NLU system looks like. So for example, the books domain will have a domain classification model that can process every utterance and provide a confidence on whether the utterance belongs to that domain or not. Similarly, they also have intent classification models that decides whether an utterance is a read book intent or a find book intent or a buy book intent and so on and so forth. And then there is a named entity recognition model that looks at the sequence of words like play Moana and then identifies which are the named entities, in this case Moana, and associates a particular named entity type like book name and a confidence for it. Similarly, the music domain has its own domain classification model, intent classification models, named entity recognizers, and so on and so forth. Now, what happens is when an utterance comes to the NLU system after the speech recognition module has processed the audio stream, each of these domains apply their models in parallel, and they generate possible interpretations of the utterance. Next, what happens is a re-ranker takes these interpretations from the different domain models and sorts them in order of confidence, and then produces a list of hypothesis interpretations for across all domains. So this illustrates how the individual domains are generating their hypothesis. And why is this architecture useful? The key is that this allows rapid scaling to support multiple domains, catering to billions of diverse utterances. Domain teams operate independently and update their models asynchronously. So what the book team needs to do to improve their experience is independent of what a music domain might need to do. And they don't have to coordinate and such. Every time they see that there is a problem they want to fix or a new feature they want to provide to the customers, they can quickly go ahead, build their own models, launch it to production, and start serving their customers. So this eliminates any cross-team dependencies and allows for rapid deployment of fixes and new features. But this architecture also creates a unique problem, which is called the domain false route problem. What is the FR problem? An utterance belonging to a particular domain X is instead routed to a different domain Y. So essentially, we misclassify the utterance. And why are these false routes hard to detect? False routes are a small fraction of overall traffic in an industry strength conversational assistant like Alexa. Just to illustrate the challenge, consider a domain X accounting for 0.5% of total traffic, and 20% of this 0.5% are FRs to other domains. That is, these false rejects account for 0.1% of overall traffic. Now, do the math. If you have billions of utterances every week, 0.1% is a very small fraction that you need to identify by sifting through all of that traffic, right? This is a classic needle in the haystack problem. So the solution we developed for identifying these false routes is based on leveraging transformer models. So what we built is a multi-layer processing pipeline that is illustrated in this figure. We take each utterance text that we saw in live traffic and encode it to a specific transformer model called Roberta. In addition, we also take the logs from our production system, like the confidence outputs from the NLU domain models and such, and then embed it into a numerical vector as well. Then what we do is we take the Roberta-based encoding as well as embeddings of the metadata, like confidence scores from the production models, concatenate them, and then feed them into a feed-forward layer with a feed-forward neural net. And then we train this full multi-stage pipeline in an end-to-end way in a multitask setting. So essentially, we are training the model to predict two things. One is a particular utterance a false route? And the second is it in the domain that we are interested in? So these illustrate the results that we were able to get. So we initially had a BiLSTM, which is another language processing model that was popular in the community a few years ago. And then we found that it has an F1 score of about 13.1, fairly low for the particular domain we were building this model for. When we moved to the transformer-based Roberta model, we saw the F1 score improve from 13.1 to 25.2. Then when we included the metadata embeddings, which is what we are calling as NBEST in this table, and trained for the single task of whether classifying a particular utterance as a false route or not, we were able to improve the F1 score further to 28.1. And then when we use the multitask setting I illustrated in the previous figure, we improved further to 30%. And then when we trained multiple such models and then aggregated their joint outputs in an ensemble, we saw a further improvement to 32.2. So overall, through our work, we improved the F1 score from 13.1 to 32.2. This work was published in ACL in 2021. And we did a further deep dive. So if you look at it in row 2, you see a Roberta-based model where we just encode the current utterance and use it to classify, versus all the other additional things we added. So if you look at the F1 scores alone, we improved from 25.2 to 32.2. which is significant. But if you actually dig deeper into the trade-off between precision and recall, we find that the simple Roberta-based model has very high precision initially. That is, it detects a whole bunch of utterances. But as we start lowering the threshold, the recall doesn't go up as much. So essentially, the Roberta-based model was identifying a lot of similar utterances initially, but was not generalizing to a broader set of false routes. But as we started making all the enhancements I just now described, we got a precision recall curve that offered a better precision versus recall trade-off at different operating points. So in terms of production impact, we leveraged the model in a human-in-the-loop offline system for false reject identification. So essentially, we applied our model at a particular operating point, identified utterances that were marked as potential false routes by the model, presented it to humans to verify if they are indeed false routes, and then used those as training examples to improve our production models. We were able to accelerate our annotation throughput by 5 times from the baseline by LSTM model. In addition, we also reduced false routes in production for the domain we targeted by an absolute 20%. We were also able to scale to multiple languages with minimal architectural languages because Roberta is an inherently multilingual model. So this is a classic example of advances in NLP community having a practical impact in a large-scale system used by millions of users every day. So the next problem we looked at is failure point isolation. Here, going back to the figure I originally showed on the multi-stage pipeline we use to process every utterance, the goal of our work is to identify which of these modules failed first when we see an erroneous response by Alexa, and then dig deeper into the problems that caused that failure. So there are many failure points in a dialogue system. As it could be false wakes, where the device woke up incorrectly. It could be an ASR error, where it produced the wrong transcription of the audio input. It could be an NLU error, maybe domain classification or intent classification, or it could be an entity resolution error, or it could also be an error in the results that were generated by the response generation component. Or finally, which is the vast majority of our utterances, is that we process the utterance correctly. So to illustrate an example of our failure point isolation, consider this figure. So in the first term, the user says, open the garage door, but the ASR module incorrectly transcribes it as open the garbage door. The NLU can process it correctly and mark the intent, the domain, as well as the entities correctly. But the entity resolution can't work. But this was not the first failure point. The first failure point was the ASR. And the user gets a defective response where we say, sorry, I couldn't find a door with the name garbage. Now consider the second example, where the user says open the garage door and ASR transcribes it as open garage door, right? The was dropped. So ASR transcription is incorrect, but it's not a failure point because the subsequent system is able to handle it correctly. And the user does not perceive a defect. Now look at the final example. The user asks something like, make me a sandwich. ASR got it right, NLU got it right, entity resolution got it right, but Alexa has to respond saying, sorry, I don't know how to do this. So the user perceives a defect, but there is no failure point in our processing system as well. So these are all different examples that we see in live traffic. So to build a failure point isolation model, we first collected a training data set with 1.5 million user requests that we split into train, dev, and testing datasets. Our dataset also included dialogues in 8 languages and was annotated by a single annotator to identify which point was a failure or if the utterance was processed correctly. We then used this training data set to train our failure point isolation model. In addition, we also collected a golden data set where we annotated 58,000 sessions using multiple annotators an ensemble of machine learning models as well to verify the annotations, and finally, an expert who looks at the labels from the models as well as annotators to finalize the final label. So this is a much more heavy duty annotation workflow that we classify as the golden data set. And all the results we represent here in this paper, in this presentation, are on this golden data set. This is also used to estimate the performance of a non-expert human annotator. So if you look at the key model components, the figure on your right illustrates what we are doing. So we have three independent processing layers. The first is the language model that takes the current utterance, the previous utterance by the user, the next utterance, as well as Alexa's responses, and encodes it in a language model. The second is a set of numerical features that we embed using a neural net model. These numerical features could be confidence scores output by different models in our processing workflow. And the final is our categorical features, like the classifier output saying the domain is a books domain or a shopping domain and the corresponding confidences. We also embed this, and then we concatenate these embeddings and then have a series of mixing layers that produce the final classification output to isolate the failure point. If you look at the results, we see that just from the language model component, we get a 40.3 F1 score. And as we start adding all of these different metadata features, we are able to improve this all the way to 51.4. How does this compare to human performance? If you look at the best model we were able to train after ensembling, we had a 53.5 F1 score, while humans had a F1 score of 57.4. That means that our model-based approach is 92.2% as accurate as our human workflow, right? So overall, to summarize, we presented a novel method for failure point isolation in these large-scale conversational assistants. We did this by training a predictive FPI model that demonstrates performance comparable to humans. We also demonstrated the importance of key model features, and our system achieves 92% of human performance while also scaling to the entire Alexa traffic, while human annotations for billions of utterances is infeasible. What are the key takeaways overall? We presented two techniques for monitoring and detecting errors in a large-scale conversational assistant. The first approach focused on one specific module, namely for natural language understanding. The second approach focused on isolating the failure points in the multi-stage pipeline to process an utterance. Both systems relied on an offline transformer-based model to detect errors in the online system. Our methods are able to scale up to large traffic volumes where human review is infeasible. Thank you very much. We look forward to hearing your feedback.
Now we'll discuss some conclusions and key takeaways. Hopefully, this tutorial has convinced you that monitoring models continuously after they're deployed can be extremely critical to ensure that the models are behaving in an expected manner. And model monitoring goes much beyond just monitoring accuracy of the models. Model monitoring also involves checking or verifying the biases and unfairness of the models continuously to ensure that there is no systematic discrimination that is being perpetrated by the models on newly encountered data. Model monitoring also involves monitoring the behavior of these deployed models via model interpretations and explanations so that we ensure that the models are not relying on spurious or irrelevant features when making predictions on newly encountered data instances. And it is also important to ensure that the models are not brittle with respect to newly encountered data instances. To this end, we need to continuously monitor the robustness of these models. And doing all these aspects continuously requires scalable frameworks and implementations. And we need to think a lot more deeply about the scalability aspect, which can be like the backbone of model monitoring in real world applications. With that, we would like to thank you all for your attention and time. Thank you so much.